Good morning. So, let us do a recap of what we learned yesterday. So, yesterday we started learning about hard and soft magnetic materials, and the reason for materials being hard or soft is coming from anisotropy. So, I told you that if you measure a property and if it depends on direction of measurement, then we say it is an anisotropy. Okay. For example, you measure the magnetic property of the material by applying field along this direction or along this direction, the hysteresis loop is going to be different. So, the properties you get like MR, MS, MS is the same, okay. MR, coercivity, all these are going to be different in different direction. Then we say that there is a magnetic anisotropy. So, we learned about a few different magnetic anisotropy. Firstly, I introduced magnetocrystalline anisotropy. Yeah. Okay. And maybe this one is hitting. Sometimes this one hits the mic. Okay. So, first type we learnt is magnetocrystalline anisotropy. So, if the magnetic atoms like cobalt, they are in certain crystallographic structure like hexagonal close pack structure, then the EZ direction is along the C axis. Okay, we haven't learnt about what is hexagonal close pack structure, what is C axis and so on. Maybe today we will do that. Okay, after we finish the remaining parts of magnetism, let us do that. Okay, time being, you imagine that let us say, okay, basically A, B axis are in the plane, C is in the vertical direction, okay, of the unit cell. So, there is an anisotropy EZ axis along the C direction. So, this is something that we learnt. Secondly, we learnt about interface anisotropy. So, instead of having a bulk very thick cobalt layer, let us say you interface cobalt with platinum. So, you split it into many layer and interface cobalt with platinum, for example. So, in this case we can see a perpendicular magnetic anisotropy. Typically a cobalt film will have EZ axis, I mean EZ direction of magnetization in the plane, but if you deposit multi layers of cobalt platinum, you can get a magnetization in the perpendicular direction. So, we can say there is a perpendicular magnetic anisotropy setting in because of the interfaces. So, this is one type of interface anisotropy. The second type we learnt that if you bring a ferromagnetic material in contact with an antiferromagnetic material and come up with some recipe. So, after you make this film according to this recipe, you will notice that the hysteresis loop is shifted from the origin by a certain field value So, we call this exchange bias field or HEB. Okay, so, in this case you see a shift, and you also see that the hysteresis loop has only one remnant state. Okay, so, this is also called unidirectional anisotropy. So, imagine that I have something like this. Okay. So, let us say imagine there is some grip which holds this pen either towards left or right. Okay. So, this grip holds the pen either towards left direction or right direction. Okay. All the other directions are unfavorable. That is what happens in the normal ferromagnetic material. So, you have two easy directions. So, it can be either this way or it can be the other way. Okay. But in the case of these systems where you have unidirectional anisotropy, only one direction is favored. Whatever I do, let us say I apply something, then it will come back to the same direction. So, only one easy direction. So, in the absence of any magnetic field, the magnetic moment is going to point only in one direction. Okay. So, that is why this name unidirectional anisotropy. Okay. Now, let us move on to the next part. Then we learnt about shape anisotropy. Okay, so, when I bring shape anisotropy, I can also discuss something about diamagnetism. Okay, these two are not related, but what I want to say is like all the materials, right, like even you take cobalt also has closed shells. Okay. So, the closed shells of cobalt atoms also will show diamagnetic property, but the diamagnetic property is overshadowed by the uncompensated spins in 3D shells. Okay. So, all the materials will show some kind of diamagnetic property, but if they have like unpaired electrons, then they will have ferromagnetic property. Ferromagnetic property will overshadow diamagnetic property. Okay. So, let me erase this whole thing. Okay, I do not want to confuse you. So, when I talk about shape anisotropy, like diamagnetism, shape anisotropy will be observable mainly in the absence of any other anisotropy. Say magnetocrystalline or some such anisotropy. Okay, when all the other anisotropy forms are very low, then we will be able to observe shape anisotropy. So, shape anisotropy determines that, let us say you magnetize a material along certain direction, the north pole and south pole must be far away. Okay. So, for an object like this, the direction is along this direction, this is hard. Okay, so, when you have a material like this is easy direction, all the other directions are hard direction. Okay. So, the rule of thumb is that the north pole and south pole formed by your magnetization should be far away from each other. Then we also learnt about some other anisotropy. Let us skip them. So, after anisotropy, then we moved on to discuss about domains. Okay. So, we started with the Heisenberg interaction, which states that the spins have to be parallel to each other, but we cannot keep too many spins parallel to each other. That will mean that the magnetostatic energy will be larger. Okay, so, if magnetostatic energy gets very large, then the system will form domains. That means, it will have some domains with opposite magnetization, but in a system it may be random. I mean, in the case of perpendicular, like you have only up domain or down domain, but if you have in plane magnetic, I mean, if there is no perpendicular anisotropy, in the in plane the magnetization can be in any direction. Okay. So, you will form various other types of domains. Okay, the system will form domains and it will also form domain walls. Domain wall is the region where the spins gradually change the direction from one domain to the other domain. So, these regions are called domain walls. Okay, so, domain walls are formed in order to minimize, I mean, you cannot increase the Heisenberg exchange energy. Okay, so, domain walls are formed to minimize the exchange energy. Okay, when you form domain walls or when you form many domains, you are forming domain walls. Which increase two energies. One is the exchange energy, because now the neighboring spins are not parallel to each other, and it also increases the anisotropy energy, because the spins are not in the direction parallel to the z axis. Okay, so, when we have domain, there are two kind of energy. One is the magnetostatic energy, the second one is domain wall energy. Okay, so, a system always wants to minimize the total energy. Okay, total energy has to be minimized. Okay. So, in some cases forming domains will minimize the magnetostatic energy a lot. It might increase the domain wall energy a bit. For example, by doing something, let us say you spend 100 rupees, but you gain 1000 rupees. Okay. Okay, you do some task A, you lose 100 rupees, gain 1000 rupees. Okay. You do task B, you lose 1000 rupees, gain 100 rupees. So, which one will you do? Obviously, this, right. So, the same thing. So, if the system will form domains if the gain which is like minimization of magnetostatic energy is a lot compared to the energy spent to form the domain walls. Okay. So, this is the one that determines whether domains will be formed or not. Okay. So, the transition point is actually the size of a particle. Okay. So, here for example, let us say I put the diameter of a particle. Let us imagine we have like some spherical particle. Okay. So, if the particles are bigger in size, so when the particles exceed some critical diameter, you will see multi-domain pattern. Your particles will be multi-domain. If the particle sizes are smaller, then you will have single domain. Okay, so, for cobalt for example, the critical value is around 50 nanometer, okay, roughly. Okay. Do not take this number for accuracy, somewhere there about 50 nanometer and above. If you make a cobalt sphere, the cobalt sphere will have multi-domain, okay. But if you make the same cobalt sphere to be of say 20 nanometer in diameter, then you will see that cobalt sphere is a single domain. Okay. So, I showed you this using the MFM images. So, I showed you the data of a tiny disk made by lithography. So, you saw that the bigger disks had many domains, and as we shrink the diameter of these tiny cylinders to 15 nanometer and below, we notice that they have single domain property. Okay. So, this is something that we learnt yesterday. After this, we started learning about magnetization reversal mechanism. Okay, the word may look very complicated. Basically, what it means is, if you bring a magnet next to a magnetic material, how the magnetic material will respond. Okay, that is basically the magnetization reversal mechanism. So, I mentioned that in some material only the region directly in the vicinity of the magnet will reverse the polarity, and in some material the reversal will spread over to very large distances. Okay. So, I mentioned that both possibilities can happen. Okay. So, when this happen, so when there is a domain wall motion, reversal mechanism happens, then you will see that your magnet influences a large region of the magnetic material below it. And this happens when you have single domain particles. So, I mentioned to you that quite often, usually whatever material you prepare, let us say you make some thin films, or you make powders, you combine them to make say some piece of magnet, okay, bulk magnet. Okay, so in all these cases usually you will find this domain wall motion reversal mechanism. So, this is the usual case. Okay. Quite often you will end up seeing this one. Only when you do some special treatments, for example, you do some chemical synthesis, you make particles. Okay, you cover these particles with some encapsulation. Let us say you have some polymer or some coating, non-magnetic coating separated from each other. So, these particles do not come closer to each other, for example. Okay. Under such cases, or you make thin films where you have magnetic grains separated from each other. So, you see there is a lot of space between the magnetic grains. Or let us say you do lithography, you make magnetic islands by lithography separated from each other and small. Okay, all this and small. Then these particles will be single domain. So, these single domain particles will undergo coherent rotation or something called Stoner-Wohlfarth reversal mechanism. Okay, Stoner is one scientist, Wohlfarth is another scientist. So, they came up with this theoretical model to explain how a single domain particle will respond to a magnetic field. Okay. So, they undergo coherent rotation. So, I showed you that in the case of domain wall motion, for example, let us say this is one domain. As you apply field, this domain will spread. Okay, so, your time t1 it is like this, t2 it has spread over larger distance, t3 it has spread even larger distance. Okay. So, that is domain wall motion, and in the case of coherent rotation, your let us say your particle has many spins. So, the spins are all parallel because it is a ferromagnetic particle, and as you apply field, these particles will go reverse together in phase. Okay, they will act as one, they will switch together. Okay, that is coherent rotation or Stoner-Wohlfarth reversal mechanism. Okay, so, in Stoner-Wohlfarth reversal mechanism, let us say a particle is in this direction, you apply certain magnetic field and the particle is in this direction. Now, you reverse the magnetic field, and only when you reach this point, when your applied field is equal to the anisotropy field of the particle, then the particle will switch magnetization to the opposite direction. Okay, again if you go from here to here, then when you reach hk, again the particle will switch the direction. Okay, so, this is what happens when you apply field in the easy direction. Let us say now I apply magnetic field in the hard direction. So, let us say I start from here. So, how will my path look like? Will it be a straight line or will it be curved? Curved. How many of you say curved? 1. How many of you say it will be a straight line? Okay, straight line is majority and winner. Okay, because we are applying magnetic field in the hard direction. Hard direction. Let us say this is the easy direction. Magnetization is like this. So, if you apply magnetic field in the hard direction, the magnetization will gradually rotate along the direction of applied field. So, as a result you will see a straight line. Okay. So, this straight line will meet this red curve at some point. So, which point it will meet? Whether it will meet here, here or here. How many of you say A? No one. How many of you say B? B, a few hands. How about C? C is majority, but B is the winner. Okay. So, in the case of Stoner-Wohlfarth reversal mechanism, the meeting point of easy and hard direction is HK. Okay. So, at H is equal to HK, the magnetization is saturated. So, yesterday I showed you 2 graphs. Okay. So, I showed you 2 graphs, one corresponding to easy direction, another graph corresponding to hard direction. So, if you look at those graphs again, I do not know whether you got the PDF files. Have you got? No. Okay. Anyway, I said to Professor Datta, he will send you the PDF of the slides. Okay. So, I had 2 graphs. So, sometime the problem is when you have 2 graphs, you do not know the relative. Okay. So, here you will notice that this point is HK. Okay. So, these 2 curves will meet at this point B. I mean, this is only for isolated nanoparticle. Okay, let us say you have another system. For example, let us say you prepare nanoparticles. So, you have a lot of nanoparticles isolated from each other. Okay, these are all single domains, but now you have a collection. Okay, here you have only one isolated nanoparticle, far away from any other particle, far away from any other particle. But normally when we make any system, right, we cannot deal with one particle. So, we will have many particles. Okay, so, this is reality. So, reality is like we have a collection of particles. So, individually each of these particles is a single domain and it will follow Stoner-Wohlfarth reversal mechanism. But when you have a collection like this, there are many interactions. For example, let us say this is magnetized in this direction. So, this generates certain magnetic field. So, this magnetic field will influence the neighboring particles and so on. So, when you have a collection, there is interaction between particles. Okay, so, this is a Stoner-Wohlfarth system, because each particle is a single domain and they are isolated from each other and so on, but still there is some interaction between these particles. Okay, so when you have such interaction, usually what happens is the particle may not reverse at this field. Okay. So, typically when you have a collection of particle, the coercivity at which say 50% particle switch is typically like half of Hk. This is a rough number. Okay. You do not pay too much emphasis to this one. So, approximately half of the anisotropy field, 50% of the particle would have reversed. Okay. If you have only one particle, that particle is supposed to reverse only at this field H is equal to Hk, but when you have many particles, like some particle reverse earlier, some particles reverse later. So, you can say half of the particles reverse at around this field. Okay, so, if I use another color to show how a group of particles may behave. So, for example, they may something like this. Okay. So, some particle reverse earlier, here some particles have reversed. So, here half of them has reversed, and at this field, the saturating field, all of them have reversed. Okay, this is a more realistic picture. Okay, we learnt that. Then what else did we learn? Then I told you about the energy landscape. So, if you plot the energy as a function of angle, so let us say this refers to one easy direction, this refers to another easy direction. The energy will be minima when the magnetization is along the easy directions. Okay. On the other hand, for any other direction, energy will be high, and along the hard direction, this is the hard direction, energy is the highest. Okay. And this height of energy is called energy barrier. And this energy barrier is given by Ku times V, where Ku is the material's anisotropy. So, it is called anisotropy constant. So, typically this is expressed in SI units, joule per cubic meter, in CGS unit, erg per cubic centimeter. So, you notice that this is energy density, energy volume density. Okay. So, this is energy per volume, you multiply by volume, you get energy. Okay. So, this KUV is the one that keeps the magnetization fixed in a particular direction. Okay, so if this energy barrier is small, you can easily change the polarity from north to south. Okay. If this barrier is very large, then you have to supply a large amount of energy to switch the magnetization. Okay. So, the coercivity of the material, for example, depends on the QUV. So, what makes a material hard or soft? Basically, the anisotropy constant. Yes. Yeah.
This energy diagram is for those interacting nanoparticles, or
this one is for isolated particle. Yeah. I mean, when you have lot of particle, then there is also another field coming in. So, it will be KUV minus some field term which is proportional to the internal field. So, every particle will see a magnetic field from the neighbors, and the energy corresponding to that field will be subtracted from KUV.
but if those like isolated nanoparticles are interacting, so like some field is acting on them, so long range order can set in. Like
No, I mean when I say some field is acting on them, it is coming from the neighboring particles, because neighboring particles have certain magnetization, right. So, they will generate a stray field.
that internal magnetic.
Yeah, internal magnetic.
Sets in order. Like, but I understand this energy diagram is like for super paramagnets. So those nanoparticles which do not interact with each other.
Okay, superparamagnetism is another case. I mean, this is for any isolated particle, you will have this one. I mean, when you have isolated particle, this energy barrier is KUV. When you have interacting particle, there will be a second term. Later when I show the slide, I will show what exactly is the term, but is some maybe m dot h or something like that. Okay. So, some energy term here that will reduce this energy barrier. So, when you have interaction, this this height may be reduced a bit. Okay. So, this reduction in the height is coming from this internal field term. Okay. So, when we talk about superparamagnetism, we are talking about the competition between KUV and the KBT. Okay, at room temperature, we have thermal energy, which is the temperature in Kelvin multiplied by Boltzmann constant. So, when this thermal energy competes with KUV, then you have superparamagnetism. So, superparamagnetism happens when the volume is very small. Okay. So, when the volume is very small, for example, your KUV also is going to be lower. So, when you have very small particles, your KUV is small. Okay, the energy barrier itself is lower. Energy barrier is lower, then thermal energy starts competing with them. As a result, the magnetization of the particle is not constant as a function of time, it flips with respect to time.
So, the particles are interacting there
In the case of superparamagnetism, the particles can interact, but at any point of time, let us say you have many particles, right. So, this particle may have magnetization in this direction, another one like this. There will be interaction, but I think it will average out unless like the other cases. So, because of this randomness in the direction of magnetization of each particle, you will see that there is no hysteresis loop. Okay. So, superparamagnetic particle will have no hysteresis loop. So, they will they will saturate, because even though the particles do not have a constant magnetization as a function of time, they still have magnetization. I mean, each particle have certain magnetic moment, because this is still ferromagnetism. So, within this small particle the spins are all parallel. So, when your applied field is very large, you will saturate all these particles along certain direction. So, they will saturate only when there is no applied field. So, in the absence of any magnetic field, the only interaction is between these two energies. So, thermal energy will make these particles to fluctuate. Mm-hmm.
The landscape is for isolated single domain particles.
Which one?
The energy landscape is
Yeah, this landscape, the orange one I draw was for the single isolated particle. So, when there is interaction, there will be this green curve, we can say. Okay, so basically this is what we learned yesterday. So, let us go through some more items, then we will have some questions. So, here I tried to show how the switching will happen. So, this is a video. So, many things happen in this picture. Okay. So, here we have magnetization and the field. So, if you look at this particular image, you will see the magnetization and the field. Here you will see the energy landscape, and here you will see the hysteresis loop. Okay. So, all aspects of Stoner-Wohlfarth is summarized in this video. So, basically you increase magnetic field. So, you can see that the magnetic field is increased from this to this angle. So, you can see that the energy landscape changes. So, this dotted line is the energy landscape in the absence of a field, but as you increase the field, you are changing the energy landscape. So, magnetization pointing along the direction of field is more stable, that is here. The other direction where magnetization is opposite to this field is unstable. Okay. Now, we are reducing the field. So, you can see this line getting shorter, this black line getting shorter. Now, magnetic field is 0, black line is somewhere here. So, we are at this point again. Now, magnetic field is going in the opposite direction. Okay. Magnitude is small. So, when this line meets here, that is H is equal to HK. Okay. So, when this black line is here, that means the applied field is equal to anisotropy field. Okay, you can see that the reversal has happened. So, now you see this one has come here, magnetization has changed direction. Now, magnetic field is 0, now magnetic field is HK. So, reversal has happened. Okay. So, I will play again, once again you can watch everything again. Okay. So, when you have many particles, single domain particles, so you can notice that as the field increases, when this field is more than the anisotropy field of certain particle, then that particle will reverse. So, in a group of particles, each particle will reverse at their own field. Okay. So, you can see that they don't switch together. So, they will switch independent of each other. Okay, so this is a cartoon of what happens when you have Stoner-Wohlfarth reversal mechanism. So, at a very high field, all the grains are saturated in one direction. When you come closer to remnants, a few of them have switched. When you are here, a few more have switched. At coercivity point, like half of them have switched, and so on. Okay. So, this is how the reversal of particles happen when they are single domains. Okay, let us do some questions now. Same as yesterday. So, it is spin week 2. So, go to wooclap.com and use the code spin week 2. Okay, majority of you are right. So, when we have isolated particles, we will have coherent rotation or Stoner-Wohlfarth reversal mechanism. Okay. Next question. Okay, how many of you are taking notes on the paper? Okay, majority of you, very good, very good. So, I can find out whether you are taking notes or not from this question. Okay. Yeah, many of you are taking notes. Okay. Yesterday I told you that the HK oops, so 2 Ku over ms. So, if you have taken notes, you would have answered this correctly. Okay. So, many of you are right. So, HK mainly depends on 2 Ku. It is inversely proportional to ms. So, this is wrong. So, 4 of you are not taking notes. Okay, so that is about magnetization, the magnetism basics. So, on 15th May we did not have time to cover this one. So, I told you that I will give a brief introduction to the material science, so that you can follow what I am going to talk in the next few weeks. Okay. So, we will do that first, then we will go on to the next chapters. Okay, materials form the era. So, you know that there is bronze era, copper era, stone era, iron era and so on, right. So, materials have played an important role in determining the way in which we live, the technology and so on. So, materials belong to various types. So, it can be metals, it can be ceramics, glasses, polymers, composites, semiconductors and so on. Okay. I mean, in the earlier days people had like only one choice. So, during the bronze era they have no access to say stainless steel or something like that. Okay. But now in this era we have access to lots of materials, and we will choose a material for a particular application depending on the performance that we want and also the cost. Okay. So, for example, to carry water you either use plastic or stainless steel, you do not use gold, right, it is very expensive. Okay. So, depending on the cost and the intended application performance, we choose different materials. Okay. So, materials belong to two types in terms of the atomic arrangement. So, one type is called crystalline. So, in many materials like metals, the atoms are arranged in certain order. Okay. So, for example, let us say these blue circles are atoms, they are arranged in a certain order. So, this periodic arrangement is what we call as lattice. Okay. And there is also long range order in some material. For example, I look at the atoms in certain place, I move several centimeter away from that location, I look at the atoms again, and if they are like almost same, then we can say that there is a long range order. So, the other type is basically non-crystalline materials or amorphous materials. So, glass, silicon oxide, these are some examples of non-crystalline materials. So, in non-crystalline materials these atoms are not arranged in order. So, you notice here the atoms are disordered. you move further away, again the arrangement is not systematic. Okay. So, you will find a disorderness in non-crystalline materials or amorphous materials. Okay. So, you cannot classify amorphous material because they are random. Okay. There is no way you can define some randomness, right. So, it will be very random whether you look here or look there, but crystalline materials have been classified into 7 crystalline systems and 14 lattice types. Okay. So, the 7 systems are cubic, tetragonal, orthorhombic, rhombohedral, hexagonal, monoclinic and triclinic. Okay. So, even I do not remember all of them, but I just want you to focus your attention on cubic and hexagonal. Okay. Because in this course you will be dealing with hexagonal crystalline structures and cubic structures. Okay. So, if you remember when I taught you magnetism, cobalt, I told you that cobalt atoms are in hexagonal structure. Okay. So, hexagonal and cubic are most relevant to this particular course. So, like me, you do not need to remember everything. Okay. So, this is how they have been classified. So, in cubic system, as you know, in a cube all the sides will be the same. So, A is equal to B is equal to C, and the angles alpha, beta, gamma are all 90 degree. So, this is the convention we use. So, we have A this direction, B is here, C is there, then alpha is the angle between B and C, beta is the angle between A and C, gamma is the angle between B and here. Okay. Gamma is here. So, this is a cubic system. So, in tetragonal system is very similar to cubic, only thing is you stretch a bit. Okay. The C is longer than A and B. Okay. All the other things are same. So, it is like if you place 2 cubes one top of another, you can say it is a tetragonal. Okay, because the C is now 2 times A. So, A is equal to B, but not equal to C is the definition for tetragonal. Orthorhombic, A, B, C all are different. Okay. The lengths are all different, but the angles are all 90 degree. Okay. So, like that you can do various types. When you come to hexagonal, you see this is how the hexagonal crystal will look like, but we take one slice. So, we take, let me draw. Okay, we just take that one slice. So, that slice will look like this. So, the A is the same, that means this length and this length are the same. C, which is this one, could be different. C is usually longer than A. And if you look at the angles, gamma is 120 degree. Okay. So, this angle, so at the bottom you have this, right. I am just looking at this one. So, this angle will be 120 degree. All the other angles are 90 degree only. Okay. So, just remember that we will be using. Okay, let me move to the next slide. Okay, so these are basically the 7 crystal lattices, and you can expand it further depending on more complex arrangements. So, in simple cubic, you have atoms only in the corners. Okay, in body centered cubic, you have atoms in the corners, and in addition, you have one atom in the center of the body of the cube. So, that is why they name body centered cubic Okay, so we will be using this name quite often, BCC. BCC means like you have 8 atoms in the corner and 1 atom in the center of the cube. Okay. Then we have another type of cube which is face centered cube. So, in this case you have 8 atoms in the corners, and in addition you have, I mean, a cube has 6 faces, right. So, in each face, the center of the face of the cube, you have 1 atom. Okay. So, face centered cubic means, let us say this is the face of a cube. Okay, you have 1 atom in the center. So, 6 faces, you have 6 atoms. Then hexagonal we already learned. So, for this course you will be looking at this hexagonal, face centered, body centered. We need to know these 3. So, in one another perspective, if you look at the hexagonal closed pack structure, you will have 7 atoms including the center atom. So, this is what we call A plane. The next plane you will have like 3 atoms, then next is similar to A. Okay, so, you will be stacking atoms like this. So, if you look at this one, so you see there are 7, right, this is another 7, but you will see 3 coming from the neighboring hexagonal structure. Okay. So, there will be A, B, C like that. So, this is A, this is C, then there is one plane coming from the neighboring hexagonal structure. Okay, so, when we talk about hexagonal structure, we say AB arrangement. Okay. FCC also is very similar, except that you have A, B, C, A and so on. So, it will have A, B, C kind of arrangement. Okay, let us do some question. Okay, let us not do question. Okay, not important. So, how can you check whether a material is crystalline or amorphous, or what kind of phase it is in? So, typically we use this device or this technique called X-ray diffraction to check whether a material is a crystalline material or amorphous, or in what kind of phase it is in, and so on. Okay. So, X-ray diffraction measurements are carried out by looking at Bragg peaks. So, we calculate the information about the crystals based on Bragg's law. Okay. So, do you know who is the youngest Nobel Prize winner? Huh? Oh, for physics. Not for the Peace Prize, but the physics. For physics, the youngest Nobel Prize winner is Bragg. Actually, this Bragg is two Braggs, Daddy Bragg and son Bragg. Okay, so son Bragg also got Nobel Prize. Okay, so they explain the X-ray diffraction based on the interference and the diffraction. Okay. So, you shine X-rays onto the crystal planes. So, there will be diffraction and there will be interference of the X-ray wave fronts, and based on this periodic arrangement, let us say the wave front that hits this plane and goes here, and this wave front, if they are in phase after this difference. Okay. So, this difference 2D whatever 2D sin theta will make the two wave fronts to be in phase. Okay. Then there will be constructive interference. Okay. So, when this condition is met, when n lambda is equal to 2D sin theta, constructive interference will take place and you will find peaks. Okay. So, when you do XRD, you will find there will be some peaks. Okay. So, if you know the lambda you know, because that is the wavelength that you used in the X-ray system, then you know the peak positions. So, these are 2 theta. So, you divide this angle by theta, you get divide by 2, you will get theta. So, substitute them, you can calculate the lattice constant d. Okay. So, for doing XRD, usually we use this 2 theta configuration. That means your sample is somewhere here, the crystal planes are here, the incident angle is theta, the refracted angle is also theta. So, in this picture you will see that there are some numbers within curly brackets, okay, 1 1 1, 2 0 0, 2 2 0 and so on. So, these numbers represents the planes which causes this diffraction and interference to happen. Okay. So, let us say this particular plane, set of planes is what gives rise to the peak here, then we have a name for it. Okay. So, those numbers are called Miller indices. So, it was proposed by this scientist William Miller. Okay. So, these Miller indices are calculated based on the reciprocal of the intersection of the plane within the cell axis. Okay. For example, let us say this is the origin. So, imagine a cube. So, the origin is somewhere inside, not in the outside, somewhere here. So, with respect to that origin, we have x, y and z directions. So, let us look at this yellow plane. Okay, this yellow plane is meeting this yellow plane is meeting x at 1, it is meeting y at 1, it is not touching the z at any time. Okay. So, we can say it is touching z at infinity. Okay. So, these are the points of intersection. Okay. So, first we write the intersection 1, 1 and infinity. So, we are talking about this plane, this yellow plane. Okay. So, the reciprocal of this will be 1, 1, 0. Okay. So, this yellow color plane, plane 2 is actually 1, 1, 0. So, similarly, you take plane 1 is meeting x at infinity, it is meeting y at 1 and it is not touching g. So, infinity 1 infinity. So, reciprocal will be something like this. Okay. So, plane 1 is 0 1 0. So, this is how we derive the Miller indices. So, when we talk about XRD, the normal brackets indicates crystalline planes and the square brackets indicate directions. Okay, we can also do transmission electron microscopy and even look at the atoms. So, here you prepare a thin piece of sample around 10 nanometer in thickness, so that electrons can go through and you can use electron as a electromagnetic wave. I mean electron is the wave for doing microscopy. So, you can look at atoms. So, in this case you can see the atoms. Okay. Okay, so you can use many techniques like XRD, transmission electron microscope, to know about the crystal property of materials. That is one thing. Secondly, as we discussed 2 days ago, the crystal material. Yes.
Can we see the atoms or can we see the planes?
We can, I mean, if your microscopy skills are good, microscope is very good, we can see the atoms. So, in the previous picture you can see all these white dots.
They are the satellite ones, not the satellite.
Pardon?
They are not the satellite ones, right? They are the atoms.
They are atoms, yes. Okay, so on day 2 we also discuss about single crystal, polycrystal materials and so on. So, the difference is, in the case of single crystalline materials, there is a long range order. So, as I mentioned, I look at some atoms, they are in certain arrangement. Sorry, my drawing is not good. So, they have certain structure, then I go like several centimeter away, then they look same. That means the order is extending over several centimeter or hundreds of millimeters. So, that is what is called single crystals. Okay. When we talk about polycrystalline material, so within certain region there is certain atomic order. Okay. So, there is some lattice within this region. So, it is crystalline, but if you go to another region, again it is crystalline, but they are in a different direction, maybe now they are like this. So, it is like the domain concept that we learned. So, we can say that this is like crystalline domain. Okay. Within small region there is a periodic arrangement, you go slightly far, there is another tiny crystal where the periodic arrangement is slightly tilted and so on. So, we have many tiny crystals. So, when we say polycrystalline, we are talking about many tiny crystals, and for this we use the term grains. So, in polycrystalline materials we have many small grains. So, within a grain itself is a small crystallite, you have atomic arrangement in a lattice, but these grains do not extend over large range. So, there is only short range. Okay. So, for some applications single crystals are used. So, many applications polycrystalline materials are also used. Okay. So, this picture shows you the difference between single crystalline, polycrystalline and amorphous material. Amorphous material, the atoms are not in any order. So, there is randomness, there is no lattice. In crystalline material there is lattice, and this lattice spreads over very large distance. In polycrystalline material there is lattice, but you can see that there is one region, then there is another region and so on. There are many tiny regions which we call grains. So, in this picture, except the white region, all the other regions are grains. So, tiny crystals like this. Okay, so, basically the polycrystalline materials will have many tiny regions. So, each region there will be periodic arrangement of atoms and there will be some grain boundary. So, these are the boundary between the grains. Okay, that is all you need to know before we move on to the next lecture. Is it time for tea or? Okay, we can break now.